Hello everybody, today I will speak about a molecular experiment, also called molecular simulation or simply theory experiment. It looks like it's not a real experiment, but there are many common points. In a real experiment, you are supposed to record everything what you've done, or conditions and so on, in a notebook, in a laboratory notebook. And of course, it's a good habit to do the same for a computer experiment. If you perform a real experiment, you should choose a method. That is a device, let us say thermostat type, or type of chromatography device, and so on. And the same in a computer experiment. Also, we have many different methods. In a real experiment, you usually build the experimental apparatus from parts. So you purchase different parts and assemble what you need. You don't do everything from scratch. And it's quite similar for a computer experiment. You can write your own computer program, but usually, especially in biochemistry, you download or buy a computer code, and often it comes in a form of blocks of code, so you must assemble what you wish from these pieces. In a real experiment, you purchase chemicals, but it may happen that some chemicals are not available, so you synthesize them. In a computer experiment, you get a force field. But sometimes it may happen that the molecule that you would like to study doesn't have a force field, or it's available only partly. So you should create your own force field for the substance you wish to study. Particularly, what is often missing are partial charges. That is, you'll take the skeleton of a molecule, that is bond length, and also Lennard-Jones parameters, angles, and so on. But then you take quantum chemistry code, like Gaussian or something like that, and calculate partial charges. Then there is preparation of the experiment in general, which means for us that you prepare the initial configurations and other part that you need to run it. Then you perform the experiment, and during the experiment you must observe what is going on. If something should be black, then it should be black and not blue, and so on. Here it's similar. You run the code, and typically you observe the time development of quantities, whether they are good or bad, and you observe the configuration, whether that looks okay. And there is analysis. So analyze the results, compile the results, put them into tables, and calculate what you wish. And here again, we usually calculate the mean values, and we must provide error or uncertainty estimates for the final values. And it's pretty similar. And if everything is done, you should clean the laboratory. And it's similar with the computer experiment. Make backups, erase all temporary files that you no longer need, and so on. And of course, we must remember to record everything. The first question is whether we should use Monte Carlo or molecular dynamics. In principle, both methods are applicable to systems which are interested in chemistry. Usually, molecular dynamics is used for realistic models and for complex molecules which bond angles, and so on, typically in biochemistry. In general, for condensed matter, it may be fluid solutions and biochemical applications, then our molecules are quite complex. From the technical point of view, molecular dynamics allows us to calculate kinetic quantities like diffusivity, viscosity, electric conductivity, heat conductivity, and so on. Also, there are more packages available, and nowadays many of them support parallelization. Parallelization either at the level of processors. A typical processor now has several threads and several CPU units. And also there are GPU, graphics processing units available, which are quite fast. And of course they are called graphics processing units because they are used for graphics, mostly for computer games, but they can be used also for calculations. It is much more difficult to program a code, but such code is available. Monte Carlo is more useful for cases of simple models, that is lattice models and very simple models of molecules like hard spheres. Also, even if we have realistic models given by a complex force field, they are often better for dilute systems. Critical phenomena, that is behavior of or near a critical point, can be better studied by Monte Carlo. Fluid equilibria, liquid-gas equilibria can be studied by special methods that are based on Monte Carlo. You'll get this equilibrium in one simulation. Also, in many simulations we need to overcome barriers. Something has very slow kinetics and we can do tricks how to overcome these barriers. For example, to exchange molecules. In molecular dynamics we cannot easily exchange molecules. Such an exchange is accompanied by a change of energy, so we need a Metropolis-like algorithm for it. A lot of this is doable also in molecular dynamics, but it's easier with Monte Carlo. It is much more difficult to parallelize Monte Carlo, and also there are fewer packages available to download and use. So, we have chosen a code, we have chosen a force field, and let's go. Of course, we wish that what we do will be accurate and correct. We have systematic errors. Of course, they are important. We may have an inaccurate molecular model or force field. It's difficult in principle to have a very accurate molecular model. Always we are doing compromises. Often we are using classical mechanics. It's much cheaper and easier. So neglecting quantum effects also brings a systematic deviation from real results. It is connected closely to neglected many body forces. That pairwise additive approximation is only an approximation. Often only small samples can be studied by simulation. That is, we may have finite size effects. Then it's possible to run several simulations and extrapolate, and it's generally difficult in some cases. Again, we have a limited time scale. It also depends on the size of the system, and the larger system, the longer correlations. Either for a large system we need long time, so all information or interaction between particles can spread through such a large system, but also they may be, for example, if we have barriers, so-called bottleneck problems, that is, it's very difficult for a system to go from one part of the configuration space to the other, like, for example, to overcome a barrier, or in general barrier of a Gibbs energy. It may be also entropically driven, not only energy driven. Typical time scales now available are microseconds, and milliseconds are the top simulations, for example, in biochemistry. We know that protein folding occurs in milliseconds, but still, for very large systems, that milliseconds are quite long simulations. Of course, we can have method problems. At a very low level, you know that the numerical integration is subject to inaccuracies. That is, our time step must be short enough, but of course, the shorter time step, the longer real time of computation. There are also problems with thermostat, barostat to choose a good one without artifacts. We should be aware of good equilibration so that we really study a system in thermodynamic equilibrium. Also, there are problems with Coulomb forces. The methods how to calculate Coulomb forces are not easy. We can do it cheaply with some systematic errors, or we can do it more accurately, and then it's more demanding. So these are systematic errors. But then there are errors which are essentially stochastic methods. These are random errors, also called stochastic or statistical errors. In simulation, we calculate one configuration from a previous one. That is, these configurations are time correlated, and also these errors are correlated in time, which must be taken into account in estimating the inaccuracies of the result. In general, these stochastic errors can be decreased for long calculations, so it's important to devise the pseudo experiment with a good length. And there is a small note about terminology. I've used term error. It's a bit confusing because we have systematic errors and stochastic or statistical errors, and we must distinguish them. This is a terminology of mathematical statistics mostly. In metrology, there is another set of terms, and term uncertainty is used. And according to the definition, uncertainty should include a critical assessment of both the systematic errors and random errors. But this is easy to say, but difficult to accomplish. Usually, what we do in pseudo experiments, we define our force field and methods. But usually it's very difficult to have an estimate of the systematic errors given by a wrong model. That is, what we provide is usually only the statistical part of the error. And I should also note that there are terminology problems in these fields. What I'm using here is mostly based on mathematical statistics, which is quite close to the statistical physics, which is the basis of this field. But in metrology and partly in physics and chemistry, people mostly use term uncertainty, in a certain simplified sense, I would say. So let's go back to the simulation methodology. Every simulation starts from certain initial configuration. In biology, we often choose the experimental structure for biomolecules like proteins and so on. You can download structures obtained usually by X-ray diffraction from databases. One of them for proteins is the so-called PDB protein database, and you get your structure in a well-described format can use it in your code, and most packages can read this format. If you study something simpler, like a liquid, then we must do several steps. Usually a liquid isn't available immediately. Either we can start from a crystal where the structure is known and melt it, or we can start from gas. Then we must shrink the box, that is to use a barostat or something like that. Also, there are methods now how to pack molecules into a box. Often they are predefined, often used structures like liquid water, so it's then easy to use. So if we don't use a crystal to simulate, let us say liquid, we can use a random configuration instead of gas. There are problems with overlaps of molecules, so in this case we should minimize the energy or to do some other tricks. Also, some models are ill-defined with respect to real random configuration, because for example, models like T4P water, also SPCE water, contain several partial charges and one Lennard-Jones term. So these partial charges are well inside the Lennard-Jones sphere. But if you have a bad luck, you can create by random shooting an unphysical configuration. This happens for this T4P model for SPCE, the negative charges at oxygen, so there can be infinities but not ill-defined configuration where it would minimize towards some problem. For lattice models, we use usually crystal or organized configuration or chaos. Also, in molecular dynamics, we need velocities. We use the so-called Maxwell-Boltzmann distribution. It is the Boltzmann distribution of kinetic energies of particles, and it is enough to have a good enough approximation, because our system during the development will create the good distribution during the development. Usually the necessary part of this molecular experiment is equilibration. We start from something which is not exactly what we want to get. Then we watch graphically different quantities in time. Here, for example, is a simulation of argon started from a crystal, and the quantity monitored is pressure. So at the very beginning, the pressure was small. That was because there was crystal. Then, with heating up the system, it went to a constant value, and here, from let us say this point, it fluctuates around a certain value, which is almost zero here. And finally, we measure the quantities of interest, including the error estimates. I will show you now a simple computer experiment. I have prepared a script for it. I will show you a preparation of a sample of liquid water. And let's try the better model, the 4B version from 2005. And it asks me for the number of molecules, so let us say 300. And let's start it from a crystal, because for the T4P it's better. So a crystal-like configuration. Now it's running. My notebook has 4 processors, so there are 4 threads available. Actually there are 8, but then it doesn't speed up. That 4 is a practical maximum. and it's finished, so I'll show you the convergence profiles of different quantities. So the first one is the total energy. The total energy decreases. The simulation contains a thermostat, particularly the Berenson thermostat, so that the total energy isn't conserved but decreases. So let's have a look at the temperature. There are 3 types of temperatures. I remember that I already told you the difference, but it's not very important at this moment. So the initial temperature went up for this was the yellow one is the translational temperature too. No, sorry, it's a rotational temperature. So yeah, it's a rotational one. So we went up to quite a high temperature, but then it cooled down by using the thermostat. And we can see that here at time, which is close to 4 picoseconds, this is in picoseconds, it is essentially leveled and fluctuating around the value which was predefined, which was 300 Kelvin. So it works. This is pressure. Again, pressure is quite, it fluctuates a lot. It is normal for small samples, but it is already equilibrated. And this is a potential energy. Essentially, it's seen a bit trend still. So it would be better to equilibrate sometime, but it's almost done. So let's go back to the simulation and continue the simulation. I've forgotten to show you the trajectory, so when it appears, I will show you the trajectory. It's here. This was the first initial configuration, so it is a crystalline configuration with possible holes, because one cannot fit 300 molecules into a regular lattice, so there must be holes, and that's why such a configuration has a high potential energy, which we've seen. If I will go by one frame, you can see that it looks very soon as a chaos, but actually it's not. We need a longer time to get the real equilibrium. If I use small balls and bonds here, you can see that this water model consists of 2 hydrogens and oxygen, and here there is an auxiliary site with a negative charge. So this model is a bit more complicated than a simple point charge model. Okay, the rest I will show you some other time. So this was one example of starting a simulation. Our simulated systems are quite small in comparison with the Avogadro number, for example, so it's necessary to be careful about the boundary conditions. The simplest case, the Cartesian space, just a normal 3-dimensional space, it's called vacuum or free boundary conditions, and it's good enough for simulating a droplet or protein in a vacuum and so on, but proteins usually don't live in a vacuum, you know. Then we often use the periodic boundary conditions. And why these conditions? Imagine that we have 1000 molecules in a cube, in a cubic system. Then if we take off just one layer at each side of such a cube, we get that inside there are only 500 molecules. That is, 1/2 of these molecules are at the boundary, and they don't behave as molecules in a liquid. So it's inefficient. That's why we use the periodic boundary conditions, or they are also called cyclic or toroidal, but periodic is nowadays the most common term. Such a simulation cell is supposed to be surrounded by replicas or copies of the same cell. So, for example, let's calculate the interaction of molecule A with other molecules. So the nearest one is D, then C, then B, it still sits in this cell, but then E. So this replica of E is closer than this one. So it's more relevant for the calculation of the interaction. Perhaps I will show you this using simulant. So I'll choose a smaller amount of molecules. Now still it's gas in a box, non-periodic, increases, and I show you color. I show another color, so I'll start random color, and now I switch to slit boundary conditions that are periodic in one dimension only. So you can see how the molecules go from one box to the other, or also I can have the fully periodic boundary conditions. Often we use different walls, or we can have different boards, that is systems which are periodic only in some dimension. Here what I showed you, these were cubic periodic boundary conditions, but we can use tessellation of space into different polyhedra. It's then more difficult, but you can find it in some packages. From the technical point of view, this is how this is implemented. You can have a look at it, but it's not too much important for this course. In Monte Carlo, it's enough to calculate the distance, so we can use a simpler trick rather than set an if here. And also, if we have a really big system, it is usually split into small cubes, and the algorithm, to be efficient, runs by slabs and by these cubes. It's called domain decomposition. Okay. But if you start any simulation, you must know how big the simulation box will be. Of course, often the simulation package can calculate a lot of stuff for you, but not everything. So let's simulate a droplet of argon in a periodic cubic simulation cell like this. And let's have 1000 atoms. And we will simulate it in periodic boundary conditions, because there is vapor here, and if we used free boundary conditions, the certain portion of the argon atoms would evaporate and it would freeze inside. So, but if this is one box, we will have another droplet of argon somewhere here, and another, let's say, here, and so on. So we must be careful that these droplets don't interact with itself. It will be interaction of a droplet with itself, so we would get quite unphysical results. So our condition will be that this droplet, considered approximately as a sphere, will be at a distance which is our condition the same as the diameter of this droplet, so that it is far enough. So let's calculate now the size of the simulation box. The data are that argon density at these conditions, we have temperature here, is about 1.4 grams per cubic centimeter, with molar mass and so on. So, how to do this? First, let's calculate the molar volume. It's given by the molar mass divided by the density. I guess it is quite easy. No problem with these calculations. Volume to one atom we'll get by dividing the molar volume by the Avogadro number, and volume of n atoms, we have 1000 of them, will be n times this. So this is the final formula for volume, and let's calculate it. Numerically, n times molar mass. Here I'm using the SI unit, so the molar mass I convert it into kilograms per mole. This is again expressed in kilograms per cubic meter, the Avogadro number, and the result is here. So let's calculate the sphere radius, that is half of the diameter, and we calculate it from this formula. This is a solution of a simple equation, and the result is here in meters. We can convert this into angstrom if you wish. It is, let us say, 2.20. Like this. And the box size is 4 times this R. That is L is 4 times the radius, and the result numerical is 90 angstroms. I will show you now how such a simulation looks like. It's a very short one. Also, you can find here the input for a computer program that calculated it. It's just to for completeness. It's nothing quite important for you. You will not work with this code. But perhaps a few notes about this, what everything is necessary to put into this code so that everything works correctly. Apparently, this is the box size, this is the number of particles, this defines how often the trajectory and protocol will be printed, this is the cutoff, I will speak about this later, the temperature, the time step, number of time steps in one cycle, because one time step is very short, so that we do not print results so often, the type of thermostat, the time constant of the thermostat, and in the first part there is an additional central force which creates the droplets from randomly chosen molecules. The first part was run using the Bernsen thermostat, then there is switched to the Anderson thermostat because it gets better the gas, and then back again with a zero central force, so we have a free droplet. And let's go back to the theory of measurements. During simulation, we calculate the so-called trajectory. It's a sequence of configurations, either in time, in molecular dynamics, or a sequence of configuration generated during Monte Carlo. Usually we observe the so-called convergence profile, or simply time development of a quantity, or it's called also time profile. There are several names of it. Here there is a typical profile of pressure during time, the blue curve. If something very wrong happens in a system, let us say a crystallization, you would immediately notice it on this time profile. But this is not the only type of profile which we draw. Some people like the cumulative time profile or convergence profile. It is the running average from the start of the simulation. So you can see that here at the very start the point is the same, and then it follows the average of everything. So it does converge. The advantage of this running average or cumulative convergence profile is that you can observe convergence and determine, at least qualitatively, the inaccuracy, the error, the statistical error of the average. But the disadvantage is that any problems in the system, that is, if it's far off equilibrium, are not so well seen. Typically, in a simulation, we get curves like this and averages of quantities. Of course, to start such a productive run means that we have already an equilibrated system. So in the first part of our project, we simulated, got an equilibrated system, and then we can start measurements. Typically, we calculate average values. We know by the ergodic hypothesis that these average values correspond to the ensemble averages. That is, we directly calculate a sample from the ensemble in Monte Carlo. In molecular dynamics, we have time development, but the average values should be the same. Less often, we calculate other quantities like fluctuations and so on. There are several types of quantities that we have, and it's useful to distinguish them by their properties. First, we have, let us say, mechanical properties. These are quantities that can be directly calculated from the configuration, that is, from particle positions and velocities. From velocities, you know that temperature is calculated. It's a bit more difficult to calculate pressure. I will come to it later, but pressure can be also calculated directly from configuration. The internal energy is equal to potential energy plus the kinetic energy. So again, it's a mechanical quantity in this sense. There are different order parameters that can be calculated, but they may be put into another bin or type. Then there are entropy quantities, like entropy and Gibbs energy, chemical potential, Helmholtz energy, and so on. These cannot be calculated by a simple average of configurations generated. They must be calculated by different approaches. I will speak about these approaches later. Then we have structural quantities. These order parameters may belong also here or here. It depends on how they are defined. And typically these are correlation functions. The correlation functions show us how particle positions or velocities and so on are correlated in space or time. Also, the number of neighbors, or the so-called coordination number, that is a typical number of neighbors to certain distance, are of this type. We can also analyze clusters by different definition and so on. And then we can have different auxiliary or control quantities. These are these order parameters, that is, if our simulation box isn't ordered somewhere, let us say there shouldn't be a dipole moment if it's a homogeneous liquid and so on. We can also study the integrals of motion in molecular dynamics, and it tells us whether our simulation is correct. In experiment, both in a computer experiment and a real experiment, we determine certain quantities and provide estimates of the values of these quantities, and these estimates should be accompanied by the estimated inaccuracy, error, or uncertainty. Typically, we estimate the mean value of a certain quantity, and then we have certain estimate of this error of this mean value. And always you should provide a quantity along with this uncertainty. The most typical estimator or measurement function in methodology called statistic, a statistic in mathematical statistics. Please note that a statistic in English is the estimator, and statistics is the field dealing with these estimators and other stuff. Czech language doesn't distinguish this. Okay, so the simplest example for determining approximately the mean value using measurements is the arithmetic average. You know it well, I believe, from physics. We have certain number of measurements, m, and we calculate its arithmetic average. Then we also define the standard error, or the standard error is defined as the standard deviation of the chosen statistic. It's usually denoted as sigma. In our case, it means we are using the definition of the standard deviation as a square root of the variance, but it's not necessary to know this. We determine the average value of the square of the difference of this statistic from the true average value. Perhaps this needs a more explanation. These measured values, it is what you imagine, what you have done. You made certain measurement, you have m, let us say now independent measurements, it doesn't have to be. You have certain number of points in a table, you can calculate using Excel such an average. Looks okay. But this is something that is called a random variable in mathematical statistics. Each individual measurement is a random variable. If you measure it, you have a trajectory or realization of this random variable. So you make an average, and it's a number for you because you had m numbers. But at a general level, this is a random variable, and this is also a random variable. You can imagine at this point that you are, let us say, 100 students in class, and everyone makes m measurements and makes the average. But these averages over all students, the averages obtained by different students will be different, because this average is again a random variable. And we can also calculate this variance, standard deviation, and so on over this averages. So then once again about the meaning of this formula. This is the true average value, the true mean value, or so-called the expectation value. But we don't know it. What we know is only this arithmetic average, in this case obtained using m individual measurements. And we calculate the average value of this. For each measurement, let us say for every student in a class of 100 students, this will be a different number. So we can define it using this huge ensemble of students where everyone made measurements. So this is a definition of standard deviation of what is inside. This squared difference. but here it is a standard deviation of our statistic, which is the arithmetic average. We can also define the standard deviation of individual value here. I'm not interested in this right now, but otherwise it's important too. Second, if we have a lot of independent random variables or individual measurements, and M is large and this has reasonable statistical properties like converging or finite average and variance, then this arithmetic average has approximately Gaussian distribution. Then also, I believe you do know this formula, the standard error of the average of these uncorrelated data is given by this formula. Here is the sum of squares of differences from the arithmetic average. And here is m minus 1. This minus 1 is sometimes called the Bessel Correction, and that's because actually here we have only this value estimated. Instead of the true average, we have only one approximation here. So we have by 1 degree of freedom less. I believe that in this or that form you know all of this, what I have said. Perhaps I'm using now a bit different terminology. So under these conditions, this is actually called the central limit theorem, but you don't have to know this term. It has certain properties. So if M is large enough, then after performing M measurements, I know that the true expectation value, the true value of the quantity is in the interval of the arithmetic average plus minus the standard deviation of this arithmetic average with probability about 67%. It follows from the Gaussian distribution. If we have 2 sigma here, the probability is a bit more than 95%. It's exactly 95% if there is 1.96 here. Wow, let's round it to a bit. Essentially, these two in practice are not distinguished. We are not so precise. Plus minus 3 sigma gives me certainty that I am within these bounds 99.7%, and in physics it's often treated 5 sigma as certainty, practical certainty, because the probability that I am wrong just by chance, by random errors is very, very small. Okay, and now about customs in different fields of science and terminology. And it's difficult. What you find in literature is certain estimate of quantity with something which is called error or uncertainty. It depends. Let us say a number plus minus another number. This is often written using parentheses, and it means that it's number 5 in the units of the least significant digit here. Okay? So that is how the number 5 is here. Some like to use a subscript here, but it is not quite clear. In other cases, this means that the true value is 123.45 and the number 5 isn't not so accurate. So I would be careful with this type of expression. It's not clearly defined what does it mean. But there is another problem. Actually, if you see this, you must know whether you are in physics or biology, because habits, what are these errors and uncertainties, depend on the branch of science. In physics, what is written here, or often here, is 1 sigma, or standard error, standard uncertainty of the quantity or of the statistic. Correctly said, this what is provided here is the estimated standard either error or uncertainty. Standard means that it's 1 sigma. Put another way, if this is an average of something, that is a mean value, it's the standard deviation of what we have, of the average, or it may be other statistic too. Loosely, you can hear different types of expressions. It's just error or uncertainty, but if you are in physics, they mean 1 sigma. They often say that it's standard deviation, but it's not enough. I must know standard deviation of what? In this case, of the average. Also, particularly if it's on a graph, it's called error bar or error margin. So typically, you have a graph here. Here is a value, and something like this here. It may be even long or different way. So when you see this on a graph in physics, it's plus or minus 1 sigma. And the custom certainty level I mentioned already, this in physics is 5 sigma. So if it was several years ago, physicists detected the Higgs boson, they had to do it in such a way that they put together all the measurements of different scattering, different decay of particles, and they accumulated a lot of events and calculated the certainty at least 5 sigma. And then they are certain that the Higgs boson was discovered. But in other branches of science, particularly in economy, or let us say drug testing, that is pharmacology, it's common to use 2 sigma, 2 standard deviations. It's more precise if we know 1.96, but actually it doesn't make sense to distinguish. This is 2 approximately. It means that the interval of confidence is at or it means that they provide here the interval of confidence at 95% confidence level. That is, other conditions are satisfied, like the Gaussian distribution. By the way, in English, Mr. Gauss was German, so I read it Gaussian. In English-speaking countries, it's often pronounced Gaussian, but I believe it's not appropriate. We should pronounce it as it is in the original country. For example, Einstein was born in Germany, so we can read his name as Einstein. But it also moved to America, and actually he had spent most of his life in the United States. So he is considered as an American physicist, and his name is pronounced as Einstein. But it makes sense, he lived in the United States. Mr. Gauss didn't live in Britain or United States. Okay, so back to the probability. This 95% confidence level, or probability that we are within these error bars, often is not considered sufficient. There are a lot of claims that we should increase this conventional level. Particularly, let us say, which is quite popular now and important, that you test a new drug. To test a new drug, you prepare a double-blind experiment and provide tests, and after all the statistics done hopefully correctly, you'll find that the new drug is efficient, it does work, gives statistically significant improvement of health at the 95 confidence level. Okay, but there is also the publication bias. Let us say that 100 of scientists in the world studies the same drug. They will do the same study using the same assay, and what may be an outcome of it? Of course, if the drug is efficient, then 95 of them should say, okay, it's efficient, and 5 or less, it depends on the level exactly, will not be able to determine it. But it may happen that the drug is not efficient. It doesn't work at all. Then just by chance, 5% in the worst case will determine the drug is efficient at the 95 confidence level, and 95 of them should say it's not efficient. If all of them published their results, it would be okay. In the literature, you would find much more results that are negative. The drug doesn't work. But it's not always the same. If something doesn't work, people don't bother to publish it. That is, there is bias for positive results, and it's dangerous. So there are claims that it's not enough. Of course, to avoid such bias, there are also so-called meta-analyses. That is, people take different results, try to combine them using statistical means, and find what's the most probable result. Okay, bad habit in these branches is that they do not provide the interval of confidence. They assume it's 95%, but it's not granted. For example, typically in a newspaper, if there are opinion polls, they say, okay, this political party is likely to be voted by, let us say, 10% of voters with interval of confidence plus minus 1, let us say, percent. But if you don't know the level, we don't know. Okay, it's 95%. I back engineered these results some time ago, so I know they use 95%, which is typical. But of course, you should know that. Unfortunately, in chemistry, the math is the worst one. Typically, the error bars are ignored at all, and if they are given, nobody knows whether it's 1 sigma or 2 sigma. So always you should specify the type of error or uncertainty that you are using. So let's proceed further with our analysis now of real simulations. The problem in simulations is that we have a time series and the individual measurements are correlated. I will show you now examples of such correlations. Here you can see uncorrelated data. These are 2,000 pieces of data, and they are pretty scattered. If I enlarge a portion of it, you can see essentially no trend. These are already correlated data. There are different types of correlation. These data are correlated in a simple way, that is, each point is given by a random number plus the previous point multiplied by something. But graphically, you can see that it's correlated. It's clearly seen. This is even more correlated. And here you can see a combination of different types of correlation. Long correlations or long scale correlations and short scale correlations added to these long range correlations. And this is what is typical in simulations. You have a short time noise, let us say thermal motion, and then you have correlation with a long time scale, for example, changes of configurations of many atoms at once, overcoming barriers, and so on. And it's difficult to handle this by statistical methods. So, in turn, we cannot use this simple formula in simulations. At least we cannot use this simple formula directly. But we can use the so-called block method. We have such correlated data like here, and we split our convergence profile or trajectory of measured data in time into blocks like this. And during every block, let us say the first block is here, we calculate the arithmetic average only over this block. Mathematically written is here. Let B, uppercase B, is the length of this block, so here we make the average, and we continue in different blocks. And then for these blocks, we can use the formula which I shown before. Then individual blocks are only little correlated. We can also proceed by the analysis of these correlations. Such correlations can be determined by means of the so-called correlation coefficients, and in turn we'll get the formula which looks like the formula I showed you before, the standard one, and here it's multiplied by something where tau is called the correlation length, but it goes beyond the scope of this talk, so I have it in gray. You don't have to know it. Actually, it's interesting that these correlation coefficients behave differently in Monte Carlo. Then they always decay exponentially, whereas in molecular dynamics, we're dynamic, so we can have oscillations. There is another quite simple method, which is essentially pretty equivalent to the block method using 10 blocks. It is a graphical method, and it is based on the running average or the cumulative convergence profile. So we draw the convergence profile. Each point is the average of all points of the time development from the start of the simulation, and it does converge. So I'll take the second half of this and calculate the difference between the maximum and minimum observed in the second half of such a cumulative convergence profile, and the sigma is approximately 1.6 times the difference maximum minus minimum. If you wish to be on the safe side and quite lazy as regards precise definitions, you can just take the maximum minus minimum. Then you have confidence level about 85%. But still, it's better to have some estimate than nothing. So 0.6 gives you something which is equivalent to 10 blocks. 10 blocks even ideal, still the distribution isn't Gaussian quite well, but if you have many data, then you'll get some reasonable information by comparing different measurements and so on. Here I have a simple example which compare different methods. I generate fake data by this formula. That is, I take a new random number, which will be Gaussian, and take the previous one, multiply by something. So this includes, introduces correlations between data, and then use all these methods and compare it with the analytical value, because now the true error estimate, the true standard deviation is known analytically. So I am not going to prove this, of course, but for testing the method, it is good enough. So here there are generated data, 4,096 pieces of data, and this is the cumulative average. So here from here, maximum minus minimum would be the estimate of the error, and to be multiplied by 0.6. Of course, the computer can do this too, so I don't have to click here. And the results are also here. The method of the second law of the running average in this case gave something that I would round up to 0.1. The exact value is a bit higher, so this is underestimated. And another method based on correlation coefficients gave a bit better value in this case. I should emphasize that this script always generates new data. So I can do it once again, and again click, and again have a look. How was this? So here actually both methods gave a pretty underestimated value, which is quite typical for few data and highly correlated series of data. So let's try it once again. Usually it works better, but I do not cheat, I show you what the method does. So here it looks better. Here one method gave pretty close. Both estimates, this one estimates a real value, so one estimates it quite well, and from the second half of the average we got a bit more. Okay, so was an example of method for correlated data. And I have here one small note about the so-called time autocorrelation function. I mentioned as something not as the mainstream when I spoke here about time correlations. So here is the time correlation function, velocity for liquid argon. And we can see that at a higher temperature, the correlations decay faster than at low temperature. And at low temperature, we can see that we have quite negative values. And this is important because it means that the sum or integral of this function, which gives me this time correlation which appears here, in molecular dynamics actually is not so high. Although these areas are not the same, this suggests that molecular dynamics for many quantities, here it's quite a quantity which is not interested because the velocity has the average value of 0, okay? But other quantities behave in a similar way. So in molecular dynamics, I can expect higher efficiency than for Monte Carlo because of this inertia. Actually, this negative value of the velocity correlation function means that my particle that goes in some direction bounces from another particle and goes back after some typical time, which is 0.3 picoseconds for argon here. Okay, so perhaps that's all what I wanted to tell you, but I repeat that this is just something to be added, not the main course. But let's go back to the error analysis. Probably you have had in physics the treatment of different measurements. The question is, I have several measurements and I will assume now that these measurements are independent. And I would like to combine these measurements in some way and get a result, but a result with the error estimate, or if you wish, uncertainty estimate. The key knowledge is that squares of standard deviations are additive. Perhaps the best way is to provide an example. So let's integrate some function using the Simpsons formula. I guess you've heard about the Simpsons formula. If not, here it's written. It's an approximation of this integral from just 3 points measured. It works fine if our function here from 0 to unity is smooth enough. Good. And let these functional values have been obtained by simulations, perhaps by some Monte Carlo integration or some simulation or whatever. And these are the results. From x is 0, here, here, and here. And our task is to calculate this value given by this formula, including the error estimate. So to calculate the value, it's easy. So just put these values into the formula, which is here, and I calculate it. No problem. But what about the errors? So I have 3 terms, and I will assume they are really independent. The first term is 1 over 6 times the value of function f at 0 argument. I will sum up squares of sigma of standard deviation of this quantity, which is 1/6 of f0. So the error estimate, the standard deviation, is 0.05 from here, divided by 6, because in the formula I have 1/6 of this value, and this squared. Please note that I have here the error estimate, the standard deviation, divided by 6, and the result is squared. And I'll do the same for the second value. The error estimate is 0.03, and the factor which I have in front of it is 4/6 squared. All errors are summed up, and I get this result, and then I will calculate the square root, and final result is here. I believe this is quite important, not only in the field of simulations, but also for a real experiment. So that's why I would like to do this in quite detail here. If we have divisions and multiplications, the squares of relative errors are additive. And again, an example is better. So let's calculate this fraction, where these are the standard deviation in the units of the least significant digits. To calculate the fraction is easy, and the relative error of this is the relative error of the first term, which is here, is this value. It means 0.07 divided by the value, and the same for the second one, the same trick, and this is the result. But this is not enough. This is the relative error. I need the absolute error, and it is the calculated fraction times this relative error here. It is 0.09. So the result, a bit rounded, will be 3.70 with the error of 0.09, or we can round it up. I don't know how to do it correctly. It depends also how this is rounded. It's safer to round it up if you wish. Similarly, we can calculate a function of a variable which is with error or uncertainty. We will use a linearized approach, that is, we expand this value using the first term of the Taylor expansion, it's plus minus the derivative times this sigma. Particularly for a logarithm, a natural logarithm, the error is in fact the relative error of the original value. For the exponential function, we have it like this. Here is the formula for the reciprocal value, and one example. Let our pH meter determined pH of certain solution here, and let's calculate the activity. First, to calculate the activity is easy. You know the definition of pH, so here is the result. Certainly you can use directly your calculator and calculate the power of 10. But for the sake of using this formula, I wrote the same expression using the exponential function, that is with the logarithm of 10. And if you use this method, I call this method 1, this formula, I take 0.05 here, so I'm using this formula, times the exponential function, but I have inside that logarithm of 10. So this is the result. Or another option is, it's a method of brute force. I calculate the activity, and I calculate the activity as if I added or subtracted this sigma to this value. Okay, and I subtract the result. It's easy to do on a calculator, and the result is essentially the same. And the final resulting activity of protons is the calculated value, and if I write it in the form in parentheses, it's 9. You can check that I am here at the same position. So thank you for your attention, and see you next time.